Okay, looking at the next part of what we have and working with the MACLAURIN series, and let's say if we have special kinds of operations like working with division and multiplication, and let's say that if you have among your functions upon which to determine the first four non-negligible terms in the MACLAURIN series, where we have starting out with f of x is equal to the sine of x times the cosine of x, as well as the sine of 2x, and also we have the tangent of x, the cotangent of x, and also we have f of x is equal to 2 to the x plus 3x squared. Okay, now the sine of 2x in itself is not a special case, but it does kind of serve a purpose in itself just for verification in line with series regarding one of our double angle formulas, and we will get to that very shortly. Okay, so we have the MACLAURIN series for the sine of x as well as for the cosine of x. And if I were to determine the MACLAURIN series of the product of the sine of x and the cosine of x, well, if I have the series for the sine of x and the cosine of x at hand, I can take the product of these series, and what I can do is do a bit of multiplication table setup, have a row column formation, where I can just have going across, let's say, the first few series terms for the sine of x, and having column arrangement. Okay, we have the first series terms from the cosine of x, and just looking at what we have in the layout. Now I could have added more terms just by adding to each of the series and attaining more products. And I did a little bit of color coding just to match the terms in the same degree, and we have just mapping together. You have 1 from the cosine of x, x from the sine of x, multiplied together, so we have the first product at x, and then for what we have upon taking, if you notice in green, you have 1 times negative 1/6 of x cubed, and simultaneously we have negative 1/2 of x squared times x. So those are the only cubic products we have in multiplying the MACLAURIN series from the sine and the cosine of x, and then multiplying what we have in the next set of terms, and we have fifth order products, okay, from multiplying the corresponding parts like 1 and 1/20 of x to the fifth, and negative 1/2 and negative 1/6 which multiplies out to 1/12, and I have x squared times x cubed is x to the fifth, and we have x times 1/24 of x to the fourth, so we have this x to the fifth product, and just continuing the trend. Okay, so we have these seventh order products, and it looks like if I had added more terms, I would have had a diagonal array of ninth order products, but just constraining it to just the first four non-negligible terms. So combining, we have x minus 2/3 of x cubed plus 2/15 of x to the fifth minus 4 3/15 of x to the seventh, and that is going to be the outcome for what we have in the MACLAURIN series whenever we are multiplying sine and cosine of x. Now, in the case of the sine of 2x, okay, nothing special here. We got the sine of x, again, we have x minus 1/6 of x cubed and so on, and wherever you see x, if we replace with 2x, just to create the backdrop in the attainment of the MACLAURIN series for the sine of 2x, and we have, again, so x, we have 2x, and we have the cube of x is the cube of 2x, which is going to be 8x cubed, and so on. And if we look at simplifying, we're going to have that the MACLAURIN series for the sine of 2x will consist of 2x minus 4/3 of x cubed plus 4/15 of x to the fifth minus 8/15 of x to the seventh. Now, one of your double angle formulas is going to be where we have the sine of 2x is equal to 2 times the product of the sine and the cosine of x. Now again, for the sine of 2x, I had this MACLAURIN series, and when we had arrived at the product of the sine and cosine of x, I had this set of terms, and if I multiply that product by 2, guess what? We're going to have the sine of 2x equal to 2 times the product of the sine of x and the cosine of x. Okay, so this is just a verification by the MACLAURIN series of our double angle property, where the sine of the double angle is equal to 2 times the product of the sine and cosine of the angle. Now, looking at what we have with the next item, and we have with the quotient function that relates sine of x and cosine of x, where sine of x is in the numerator, cosine in the denominator. We have the tangent function, and in Maclaurin series terms. Now the tangent of x is going to be the quotient, again, sine of x divided by cosine of x. And if you look at the Maclaurin series terms, and if I were to establish a Maclaurin series for the tangent of x, I would be looking at taking the Maclaurin series of the cosine of x into that sine of x, and just look at, instead of the conventional descending degree arrangement between the divisor and the dividend, we're actually going with ascending degree, because that is just how the Maclaurin series are arranged. Okay, so if you notice, you have cosine into sine. Looking at the leading terms, you have 1 into x will go x times, so that would be the first term in the quotient. And with the long division, we have the leading term in the next step is 1/3 of x cubed, and 1 into 1/3 of x cubed is going to be 1/3 of x cubed, which will be the second term. And following, okay, we have the next leading term is going to be 2/15 of x to the 5th, and that's going to be the third term of the quotient. And just limiting again to just the first 4 terms, and the fourth of which is going to be 17/3/15 of x to the 7th. And we have from the long division with these first 4 terms, we're going to have those to be among the first items of what we have for the tangent of x. And again, this is continuous series where we have the first terms to consist of x, 1/3 of x cubed, 2/15 of x to the 5th, and 17/3/15 of x to the 7th. And the other quotient identity where we have tying in together sine and cosine is where we have the reciprocal of the tangent, which is going to be the cotangent of x. And if we put what we have in Maclaurin series terms, the cotangent of x, so I'm taking the Maclaurin series of the sine of x into cosine of x. So looking at taking x into 1, well, this is only going to be the reciprocal of x. And if I distribute, we have our first leading term after the first round of long division to be negative 1/3 of x squared. And taking x into negative 1/3 of x squared, we have minus 1/3 of x. And then distributing over the first 4 terms from the sine of x, and then subtracting, we have the next leading term at negative 1/45 of x to the 4th. X into that is going to be negative 1/45 of x cubed. Go through the round, and we have for the 4th term in the quotient will be x into negative 2 9/45 of x to the 6th. So we have negative 2 9/45 of x to the 5th. And so we have for the cotangent of x, we have 1 over x minus 1/3 of x minus 1/45 of x cubed minus 2 9/45 of x to the 5th. And we have also in the mix, now let's say if you have an exponential and a quadratic term added together, like in the case of f of x is equal to 2 raised to the x added to 3x squared. Okay, now going back to our Maclaurin series definition. Okay, so if we look at taking our function, we have f of x equal to 2 to the x plus 3x squared. And if I take the first order derivative, now the first order derivative, if you recall from calculus, the derivative of a to the x is going to be a to the x times the natural logarithm of a. And with a at 2, we have 2 to the x times the natural logarithm of 2. And the first order derivative of 3x squared comes out to 6x. And for the second order derivative, you're going to have, like, think of like the product rule. Okay, you have natural logarithm of 2 times the derivative of 2 to the x, and guess what? It'll be a natural logarithm of 2 times 2 to the x times the natural logarithm of 2. So you have the result at 2 to the x times the square of the natural logarithm of 2. And we have for the derivative of 6x, that will come out to 6. And then the derivative of 6 goes to 0, and the derivative of 2 to the x times the square of the natural logarithm of 2, and we're just taking the derivative of 2 to the x once more and multiplying by the square of the natural logarithm of 2. So we come out to 2 to the x times the cube of the natural logarithm of 2. And for each of these function values and their derivatives, whenever x is set to 0, where we have 2 to the 0 plus 0 comes out to 1. And we have first order derivative whenever x is equal to 0, we have the natural logarithm of 2. Second order derivative, we have the square of the natural logarithm of 2 plus 6. And you can write this as like ln squared of 2. It's kind of like a shorthand notation, followed by the addition of 6. And likewise, for the third order derivative, we have the cube of the natural logarithm of 2. You can write that as ln to the third of 2, like the cube of the natural logarithm of 2. Kind of like square of cosine of x is cosine of x quantity squared. Same kind of notation. And going back to what we have with the definition of MACLAURIN series, and again, so your f of 0 is going to be 1, f prime of 0 is going to be the natural logarithm of 2 and multiplied by x, and we can write this as x natural logarithm of 2. And with the second order derivative terms multiplied by x squared, we can say we have x squared times the quantity of the addition between the square of the natural logarithm of 2 and 6 all over 2. And then we have with the fourth term, we can say we have x cubed times the cube of the natural logarithm of 2 all over 6. And again, this is going to become a continuous series in the process. And so those are samples of what we have in working with the MACLAURIN series, where you might have special cases of multiplication and division, and potentially where you might have exponential functions.